Welcome to this very detailed explainer, where we are going to completely break down the hardware-software bridge of accelerated computing. Think about this for a second. A really high-end CPU might process, 16 to 24 threads simultaneously? But a modern GPU can launch tens of thousands of threads at the exact same moment to just absolutely crush through data. Today, we're taking a masterclass approach to look closely at the fundamental mechanics that allow standard code to seamlessly pass the baton over to these massive parallel processors. Here's our roadmap for today's masterclass. 1. The masterclass in parallel computing. 2. CPU versus GPU architecture. 3. The CUDA execution model. 4. GPU acceleration with NVIDIA. And 5. Mastering device memory transfers. All right, let's jump right into part 1, the masterclass in parallel computing, setting the foundations of acceleration. Traditionally, if you wanted to master CUDA, you needed some pretty deep expertise in C and C++, computer organization, and operating systems. To really understand how a CPU talks to a GPU using standard CUDA C++, you essentially have to know how memory is allocated on a raw physical level. You're dealing with manual pointers and explicit, highly complex low-level hardware control, which honestly is incredibly difficult to manage safely. Establishing this baseline is vital because it explains exactly why GPU programming was historically reserved purely for low-level systems engineers. Moving on to part 2, CPU versus GPU architecture, the manager and the factory floor. Think of your system as a heterogeneous computing architecture. The CPU is the manager handling the overarching control, and the GPU is the factory floor doing the compute-intensive heavy lifting. The CPU is absolutely incredible at jumping between entirely different types of tasks, managing your operating system, responding to inputs, and executing sequential logic operations. That's the control side. The GPU, on the other hand, is a highly specialized worker. It thrives, and I mean absolutely thrives, when you give it massive, computationally intensive mathematical tasks that can be broken down and solved all at the exact same time. Let's bust a pretty common myth right now. A GPU is not a standalone, super smart brain. It just isn't. Your GPU doesn't run your operating system, and it definitely doesn't make autonomous decisions on what you compute. It literally just sits there, waiting for the CPU to hand it a specific, highly parallelizable job. It acts strictly as an accelerator.
Because it takes orders directly from the CPU, its physical architecture is vastly different. A top-tier CPU might have 16 or maybe 24 highly complex cores designed for intricate sequential logic. Well, the GPU sacrifices all of that complex control logic to pack in literally over 16,000 simpler cores. When the CPU gives the command, the GPU can launch millions of threads across these thousands of cores to crush through data like an endless factory assembly line.
Which brings us to part 3. The CUDA execution model, step-by-step hardware execution. Getting that data from the manager to the factory floor is a highly deliberate, carefully orchestrated dance. First, memory has to be allocated on both the main CPU and the distinct GPU memory space. Then, data is physically copied over the hardware bridge from the CPU directly into the GPU. Only then does the CPU instruct the GPU to actually start executing its parallel tasks. And it doesn't end there. After the math is done, the results have to be copied all the way back across that exact same hardware bridge to the CPU memory before finally freeing up the space.
We can actually take that complex 9-stage process and distill it down into a highly digestible 5-step masterclass framework. Whether you are writing low-level C code or high-level Python, the hardware always enforces this exact sequence. You allocate, you transfer in, you execute, you transfer out, and you clean up. Memorizing this physical flow is absolutely crucial to mastering GPU acceleration, mostly because it highlights exactly where your program might suddenly hit a wall and slow down.
Okay, part 4, GPU acceleration with NVIDIA, bypassing C and C++ in Python. Enter NVIDIA. This is an incredibly attractive tool for Python programmers who want to accelerate element-wise NumPy array functions without ever having to touch C or C++. It acts as a just-in-time or JIT compiler. Basically, that means it compiles your standard, highly readable Python functions into raw machine code on the fly at execution time so the GPU can instantly process it. You get the massive parallel power of the GPU architecture we just discussed, but you get to stay entirely within the comfortable confines of Python.
So where does this fit into the broader ecosystem? Well, while CUDA C++ remains the most flexible industry standard, Numba sits right alongside PyCUDA as a highly accessible option for Python developers. CUDA C++ is undeniably the most performant way to code because it gives you absolute granular control over every single aspect of the hardware. But Numba is perfect when your focus is strictly on numeric acceleration. It abstracts away a lot of that heavy boilerplate we saw in the execution model, allowing you to focus purely on the mathematics.
And finally, Part 5. Mastering device memory transfers, avoiding the bottleneck. Here is where things can go really wrong. Whenever your code forces the hardware to implicitly copy data back and forth between the CPU and the GPU, you create a massive bottleneck that absolutely kills your performance. Remember that physical bridge between the CPU memory and GPU memory we detailed earlier? Sending data across that bridge is incredibly slow compared to the lightning-fast calculation speeds of the GPU cores themselves. If your code is secretly making round trips across this bridge for every little calculation, your GPU will just spend all its time waiting for data to arrive, which completely negates the benefits of using an accelerator in the first place. So this is where you step in and take back control. By manually telling Numba to create an output buffer natively on the device using numba.cuda.device_array, you keep the data permanently on the factory floor. The GPU can write its results directly into this local space without triggering a costly implicit transfer back to the CPU manager. The data stays on the GPU until you, the programmer, explicitly call for it to come back to main memory.
The source material leaves us with a very strict rule, and it's one you really need to internalize. Always measure your data transfer times to ensure your optimization is actually helping. It is such a common trap to assume that simply pushing a function over to the GPU will automatically make it faster. But if the data transfer time across that host-to-device bridge takes longer than the math would have taken on a standard CPU, you've actually degraded your overall performance. Benchmarking isn't optional. It's absolutely non-negotiable.
I want to leave you with this final provocative thought for your next project, challenging you to really analyze if your computationally heavy functions truly justify the memory transit costs. Acceleration is an incredible tool, but it requires a strategic mind. You now know the physical hardware architecture, the strict execution model, and the hidden bottlenecks. So the next time you write a function, ask yourself, is the math heavy enough to make the trip worth it? Thank you for joining this explainer and keep building smarter code.